right, let's try and get started. So we make sure that we have the time. Looks like we got some folks sitting on the floor. We got some empty seats in different places, so if you don't want to sit on the floor, we definitely have some seats out there. We got one down here, a couple down here, some right up here. So. I don't actually spit that much either, so you'll be okay. For this review, the way I run my reviews, I don't know how Dr. Deschamps did his, and I don't think Dr. Grumshaw ran one this time around, because we are already doing two. I'll just go through the set of practice problems that we've got up on D2L, and I'm just going to go through them one at a time and just ask if you want to see that one. If you want to see that one, say yes. If you don't, you just be quiet. And if I don't hear anything to that problem, I'm just going to move on to the next one then, so that we're not wasting time on any of the problems that we don't need to do.
Will we be getting the constancy?
On the exam? Or now?
Tomorrow on the exam.
Yeah, on the exam. Yeah, it's already posted on the draw. Yeah, if you go into content, it'll have content.
I was just wondering if you're going to give it to us tomorrow as soon as the exam.
Yeah. That's what you're going to get is posted on D2L. Yeah. But yes, it will be physically on the exam as well.
Okay, thank you.
Yeah. All right. So I am recording this as well, so if you want to go back and watch this tomorrow, you can do that as well. So we'll just get started here. Number one. All right, we'll be out of here in 5 minutes. Number two. Yes. Okay, so number two says read the water level with the correct number of significant figures. So that's kind of that's really a pertinent one because we do read a lot of instrumentation here. And so this one won't show up from the pen at all, but I'll put it on. Go ahead and put it on here. So notice that we've got marks here. We've got an 87 and an 88 here. And we've got 10th markings in between there. So from the markings alone, we can read 86 or 87.1, 87.2, 87.3, 87.4. And then if the line is between those, we can estimate one more digit. So we can actually go to the hundredths place, because that's our least significant, that's our estimated digit there. So the markings go to the 10th, and then we can estimate one more digit past that. So this one looks like it's right on the 2/10ths mark, and so we would say 87.20, not just 87.2. We would say you can see that it's right on the mark, and so we have that additional zero. We do have some chairs and stuff down along here, along near the front, if you don't want to sit on the floor. Okay, so that one would be A, 87.20. I should probably check to make sure that's the answer, and it is. Okay, everybody good at that one? Okay, number three. Yep, sorry. You want to see number three? Okay, so, say something if you want to say it. Just say yes. Don't be afraid of somebody hearing you say yes. So how many significant figures are in the measurement? 20.300 meters. So we've got a lot of zeros in there. So remember, as soon as we get to a number that's not zero, we start counting our significant figures. Okay? And then, if we have numbers in front of a decimal point and after the decimal point, then all those numbers are going to be significant. So in this case, the 20.300 are all significant values there. Those are all measured numbers. If we have that zero, there's two zeros that appear after a decimal point and after a non-zero number. If those two conditions are met, then those zeros are always significant. So this one would actually be 5 significant figures. Okay, 5 significant figures on that. Questions on that one at all? All right. Number 4. Okay, so factor 10 to the 9th. What do we call that 10 to the 9th? What's the word for it? It's giga. Okay, not 10 to the minus 9, but 10 to the 9th. So that's a giga, like a gigabyte. In computer terms, is 10 to the 9th bytes, or a billion bytes, and so we use a capital G for that. So that's giga. If it were 10 to the minus 9, what would that be? Yeah, would be an N for nano. Okay, N for nano. And that wasn't one of the options. So I hope that was the answer, was A on that. Yeah. All right. Number 5.
Yes.
Yes. Excellent. So what decimal power does the abbreviation P represent? And so P is what? It's either pico or pico. And so if you look that up, it's 10 to the minus 12. 10 to the minus 12. So nano is 10 to the minus 9. Pico goes one more than that, 10 to the minus 12. It's another power of 3. You'll notice most of our major marks tend to go in the minus 3. We have milli at 10 to the minus 3, micro 10 to the minus 6, nano 10 to the minus 9, pico 10 to the minus 12. Okay, so those are your most common ones. Questions on that one? Yes?
How far in the SI prefix series do you know?
That would be as far down as I would expect. Yeah. And giga is about as far up as I would expect. We really never even use giga very often. We don't use the big ones very often, unless we're dealing with frequency and we're in like megahertz or gigahertz. But that's about it. Yeah, I would never give you a gigagram or anything weird because that's just not something you see. So, yeah, I'm not going to start making up weird measurements just to mess with you on the page. Let's see. Number 6. Yes. So determine the mass of a metal cube that has a density of 12.7 grams per milliliter and a volume of 87.63 milliliters. So let's take a look at that one. So we know that. So let me write 6. So I know that density is equal to mass over volume. Okay, and I'm not looking for density though, I'm looking for mass. So let's rearrange this one. So I'm going to multiply both sides by volume there, and I'm going to get volume times density is equal to mass. So now I have a mass equals equation, and it's volume times density. So if I take my volume, we'll say mass equals 87.63 milliliters times 12.7 grams per 1 milliliter. And I like writing my conversion factors like that. Grams per 1 of whatever. Grams per 1 milliliter. So this allows my milliliters to cancel out. I get 87.63 times 12.7. The only unit I have left is grams. And that comes out to be 1112 grams. We only get 3 significant figures there because of the 12.7, and so they put that in scientific notation at 1.11 times 10 to the third grams. Okay, questions on that? All right. For those of you just coming in, we've still got seats in various places if you don't want to stand or sit on the floor. There's a lot down here in front. And I don't bite much. Number 7. Yes. So that was number 7. I know I didn't really talk much about in class that conversion. It's a really simple conversion. We haven't had to do much of it, but it was in your reading. So I just went ahead and threw a problem in there. Just converting Celsius into Kelvin. And so for Celsius into Kelvin, your Kelvin temperature is equal to degrees Celsius plus 273. Okay, I guess it's not really just plus 273. Sometimes you'll see 273.15. We don't normally need to go quite that specific for our temperature. And so our Kelvin temperature here is just going to be our Celsius temperature, 125 degrees Celsius plus 273, and we end up with the temperature of 398 Kelvin. Once we start using temperature in our equations, which we will eventually get into, we do that conversion a lot because we're usually measuring our temperatures in Celsius, but then our equations need to use it in Kelvin because it's an absolute temperature. It keeps our temperatures from becoming negative. Okay, questions at all on that one? Questions? Okay. Number 8. Good. Number 9. Yes. So we're looking for the pure substance from the list below. So remember when we were looking at classifying matter, our pure substances were either our elements or our compounds. Okay, so, oh man, that's my favorite song. Do, 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 do. Yeah, I shouldn't have done that while I'm recording this. That's out of there. Alright, so choose a pure substance. So the answer there is A, carbon dioxide. It has a chemical formula CO2. It's always CO2. It's a compound, so it has carbon and 2 oxygens on there, and that's what makes it a pure substance. Casserole is a casserole of pure substance. Now, casseroles can pretty much be just about anything, and you probably have experience with that as well, if your moms love casseroles. What about pomegranate juice? Is that a pure substance? Now, it's got all kinds of different stuff in there. What would we call pomegranate juice? Some sort of mixture, either homogeneous or heterogeneous, depending on whether it was filtered or not. If it's got floaties in it, it's definitely heterogeneous. What about coffee? Coffee would also be a mixture. It'd be a mixture. It's got water in there, it's got caffeine, it's got coffee dew, whatever makes coffee taste like coffee. What about salt water? Also a mixture. If it's just salt and water, that'd be a homogeneous mixture. If it's like salt water out of the ocean, then you got seaweed and fish poop in it, and it's heterogeneous. Once again, recording. I gotta watch that. All right. So is that one making sense? So it could be elemental or compound to be a pure substance. Number 10. We're good. Concept of atomic number. Good. Number 11. Yeah, I knew that was coming. All right, so new compound was recently discovered. Actually, they shouldn't have said compound. They should have said element. Was recently discovered, found to have an atomic weight of 342.38 AMUs. This element has 2 isotopes, the lighter of which has a mass of 340.91 AMUs and an abundance of 68.322. What is the mass of the heavier isotope? Okay. So remember, to get our average mass, we use the weighted average of the isotopes. And we're told we only have 2 isotopes. We're given the abundance of one of those. So let's do number 11 here. And so we know that our average is 342.38, and that's AMUs. So that's going to be equal to, and we're going to take each mass times its weighted average its abundance as a decimal, as a fraction, okay, as opposed to a percent. So we know that we've got a 340.91 AMU. And its abundance is 68.322%, so 0.68322. So that's its fraction of abundance. Okay. Now, if I only have one other isotope, what is the other fraction for the other abundance? How would I find that? Just 1 minus that, or 100 minus the percentage, either one. Since we want the fraction, let's do 1 minus. And so we're going to add that to this. So we don't know the AMUs of that heavier isotope, but we do know its abundance here. And so that's going to be 0.31678. Okay, and again, I got that value by taking 1 minus the 0.68322. Well, now I just have one variable there. I just have one unknown, and I've got one equation, so I can solve that. And so when I solve this, I end up with an x value of 345.55 AMUs. And so that would be choice E. Okay, so I would just multiply this by this, get a value, subtract it from here, and then divide by that abundance to isolate x by itself. Make sure that you can do that math. Make sure you can isolate that variable there. Any questions at all on that one? Yeah?
How did you get the decimal plus multiply by the x minus 6?
So that's my other fractional abundance, and so that's 1 minus the 0.683. So that's the percentage of that element, or that isotope expressed as a decimal. Anything else on that one? Okay. Look at that, down at the first page. Number 12. It can be broken down to simpler substances as you know it. Number 13. Some definitional memorization stuff on that. Good. Number 14. Yes. Okay, so we want to know, what does X represent in the following symbol? I did not bring a periodic table with me. I thought about it, and then I ended up saying, no, I don't think I need it. Yeah, I do need it. So that's okay, we'll talk about it. So we've got 80, 35, and X there. So we just want to know, what is X? What element does X represent there? Okay, remember that this value right there, that 35, what is that? Yep, that's my atomic number, which is also the number of protons in there. Okay, but where can I find what element belongs to what atomic number? On the periodic table, I look across those top numbers, I find number 35, and when I find number 35, I see that it is in fact bromine there. Okay, so that's how I do that. What would I do with that 80? What is the 80 up there? No, that's not the atomic mass. 80 is my mass number. Don't confuse those two, because they are different. Okay, the atomic mass was what we just calculated in 11, where we have the abundances times the mass of each isotope. The atomic mass, or the mass number, is the number of protons plus neutrons. Protons plus neutrons. So if we wanted to, we can figure out how many neutrons were in that isotope. It didn't ask for that, but we could have done it. Okay, so we said this was bromine, right? Yeah. All right. How about number 15? Yes? Yes? Okay, sorry. So 15. So we've got 65 there, 29 there, and X. So once again, we don't know what element it is. We don't care. It's not asking for the element. It wants to know all the different particles in there. Okay, so once again, what can we get immediately from that 29? It's the number of protons. So protons is going to be equal to 29. Now also, related to the protons, notice that there is no charge written on that element. So we've got an atom. And if I have 29 protons, what else must I have? 29 electrons. I've got to have the same number of positives and negatives there. So I know that I've got 29 electrons, and now I just need to figure out the number of neutrons. Okay, so I know that 65 is equal to my protons plus neutrons. So I know my number of protons is 29, and that means that N must equal 36. And so that would be choice A, with 29 protons, 36 neutrons, and 29 electrons. All right. What do you find at a family reunion of Nickelodeon cartoons? 36 neutrons. Jimmy Neutron is great. I know it was bad. I used to love watching Jimmy Neutron. It's hard to even find reruns anymore. All right, number 16. Yes, so what species is represented by the following information. So another very similar problem to what we just did. Okay, so we're told that we've got 17 protons. We've got 18 neutrons. And we've got 18 electrons. Okay, well, if I've got 17 protons, what element do I have? Yeah, we find atomic number 17 in the periodic table, and that tells us that we have chlorine as an element, but notice that my number of protons and my number of electrons are out of balance. I have an extra electron in there, and that means that I now have an ion. This is going to have a -1 charge on it. Okay, so I should get E there, Cl minus. If I had one fewer electron, if I only had 17 electrons, then I would have a chlorine atom. But because I have 18 electrons, I have a chlorine anion. I have that negative charge on it. Questions at all on that one? All right. Number 17. Yep, I figured 17 was coming. 17 is similar to the one we did in the previous page. Although here we're just looking to calculate that average atomic mass there. We have the abundances. So on number 17, we're going to convert our percentages into fractional amounts, decimal fraction amounts. So we're going to say that our atomic mass... Yep, I'll get it. Actually, it's just easier to move this down. There we go. So my atomic mass is going to be equal to each isotope mass. So we're going to have 68.9256 times its abundance percentage as a fraction, so 0.6011. And then we're going to add the other isotope mass, so 70.9247 times its abundance, which is 0.3989. And when we calculate all of that out, we end up with 69.72. Since our percentages just have 4 to 6 that's all we're allowed in this problem. So 69.72, which is choice D. Questions at all on anything I did on that? Number 18. Yes. So, number 18 says, what mass in milligrams does 2.63 moles of nickel have? Okay, so if we look at nickel, well, we're told we have 2.63 moles of nickel, and we know from the periodic table that the atomic mass on the bottom of an element is not only the mass of one atom in AMUs, it's the mass of 1 mole of that substance in grams. And so that's our grams per 1 mole, molar mass. So for our nickel here, I'm going to do number 18. So we're going to write down first what we know. So we have 2.63 moles. And now we're going to multiply that by our conversion factor. Now, for our conversion factor for nickel, we have 58.69 grams per 1 mole, or I could write it as 1 mole per 58.69 grams. Which of those two conversion factors do I want to use? I want the first one because I want those moles to cancel out. Okay, so I'm going to have 58.69 grams per 1 mole. My moles are gone, and I end up with 154.35 grams, but it didn't ask for it in grams, did it? It asked for it in milligrams. You've got to watch that on some of those problems, especially in the practice ones. So now I'm going to convert my grams into milligrams. So I have 154.35 grams times, and now I can do 1,000 milligrams per 1 gram, or 1 gram per 1,000 milligrams. Which of those do I want to use, first or second? It's the first one again, because I want my grams to cancel. So times 1,000 milligrams per 1 gram, my grams cancel, and you end up with a really big number that they put into scientific notation. So that's going to be 1.54 times 10 to the 5th milligrams. Okay, you'll notice that I like to use one of the larger unit, grams, and then get a large number of the small units. So we have 1 gram per 1,000 milligrams. I know the book would rather have one of the smaller units and then a fractional negative exponent of the larger unit. So they would have 10 to the minus 3 grams per 1 milligram. They're identical. There's no difference in the answer you would get. It's just what you prefer. I prefer it that way. So it's the same thing, it's just different values, but the same ratios. Questions at all? Questions? That was 18. 19. Okay, good. Amplitude. Number 20. Yes? Okay, you've got to be loud because there's a lot of ambient noise down there. So we're looking for colors of light with the highest frequency. And so some of this is just memorization as far as what we have on the electromagnetic frequency or electromagnetic radiation chart there. And so we have our old buddy there that tells us the colors of light. We have Roy G. Biv. Okay? Red being the longest of the wavelengths, violet being the shortest. Okay? So if we know that red has the longest wavelength, what does that tell me about the frequency? It's low frequency. Remember, wavelength and frequency are kind of opposites there. Okay? So our shortest wavelength there is going to be blue, and the shortest wavelength is going to have the highest frequency. And so that's why blue is the answer there. So the shortest wavelength is going to have the highest frequency. Because it's going to go up and down the most times as it travels by, as opposed to a really long wavelength like this. Does that make sense to everybody? How about 21? Well, now it's kind of easier, isn't it? Because now we're just looking for the shortest wavelength. And again, Roy G. Biv, you can remember that red is long, and violet is short. That'll help you with energy, it'll help you with frequency, it'll help you with the wavelength, because they're all related. So the shortest wavelength there is going to be violet, because that's our B of Biv on there. So that's our shortest wavelength. Shorter even than blue. Okay? Questions on that one? If you have a hard time remembering which goes where, it's a great thing to put on your note card. Okay? 22. Yes. So we want to calculate the wavelength in nanometers of blue light emitted by a mercury lamp with a frequency of 6.88 times 10 to the 14th hertz. So we're given a frequency and we're looking for wavelength. Okay, so let's write down what we know first. So we know the frequency. So nu is equal to 6.88 times 10 to the 14th hertz, which is also equal to the unit of 1 over second. So 1 over seconds is a hertz. You guys ever hear of a Hertz donut? You ask people, like, you ever hear of a Hertz donut? And they go, no. And you punch them in the arm and you go, Hertz donut. I got 2 older brothers, can you tell? I remember the days. All right, so that's really all we know. Well, we know we're dealing with light. And so we know that the value of C for light is 3.00 times 10 to the 8th meters per second. And we're looking for the wavelength in nanometers. All right. So do we have an equation that relates C, frequency, and wavelength? We do. Okay, we know that C is equal to frequency times wavelength. Oh, that's a nice equation. But we're looking for wavelength, so let's rearrange that to solve for wavelength. And so that's going to give us wavelength is equal to C over frequency. And so we can plug everything in there. We have 3.00 times 10 to the 8th meters per second over 6.88 times 10 to the 14th. And I'm going to do 1 over seconds here, because my 1 over seconds here is going to cancel with the over seconds there, and it's going to leave me only with the unit of meters. And I get a value of meters of 4.36 times 10 to the minus 7 meters. Now the question asked for nanometers, so let's go ahead and convert that. So now we're going to take that answer and we're going to say 4.36 times 10 to the minus 7 nanometers times, and we're going to do 10 to the 9th nanometers for every 1 meter. Again, I like having a much larger number of the tiny unit, just 1 of the big unit. And a meter is much bigger than a nanometer. Did I do that right? Yeah, what did I do wrong there? Oh, thank you. I was like, wait a minute, that's going to work out mathematically. What did I do with my units? Yeah, thank you. It's meters, not nanometers there. So my meters cancel, and so that leaves me with 436 nanometers. Any questions on it? Yes? It's hertz to 1 over second. They're identical units. Yeah, a hertz is a 1 over second unit. It's what it means. So it was named in honor of Hertz, but its unit is 1 over second. All right, good one. Questions on that one? Any other questions on that? All right, 23. Yes? Okay, so which of the following occurs as the wavelength of a photon increases? Well, we've got a couple of different equations that involve wavelength. So let's write what those are. So we know that we have C is equal to frequency times wavelength. And we also know that E is equal to HC over wavelength. Okay, so as wavelength increases, okay, so we know that C is a what? It's a constant speed of light. And so if my frequency goes up, if my wavelength goes up, in order to keep C, to make that side equal C, what has to happen to my frequency? Frequency's got to go down. Okay, if you've got 2 numbers multiplied by each other equaling a constant, one of those numbers goes up, the other number has to go down. Okay, it's kind of like if you have a constant that's equal to the number 12, and you have 3 times 4, if this one goes up to 6, this one has to become 2. So I still have the same quotient, or the same product there. Okay, good. So that's why A is the answer. Let's look at energy. So if my wavelength increases, I'm increasing the denominator in a fraction. What happens as you increase the denominator in a fraction? What happens to the value of the fraction? It goes down. That's why 1/4 is smaller than a third, 1/5 is smaller than a fourth, 1/6 is smaller than a fifth, etc. As that number in the denominator gets bigger, then the whole value of the fraction goes down. So that's not right. Planck's constant decreases. Well, do constants increase or decrease? No, otherwise it wouldn't be constant. You can call me a liar about that later in the course when we have constants that change, which I think is stupid, but it happens. But they're not named constants like that, they're reaction-specific constants. So Planck's constant never changes. What about the speed? Is the speed going to decrease? No, because we're dealing with light. The speed of light's a constant as well, so that can't change. Okay, good. So correct answer there was A. 24. Okay, so 24 is just E. All of those are true up there. So the uncertainty principle, so Heisenberg uncertainty principle, states that we can never know both the exact location and speed of an electron. Now, it actually says momentum, which is mass times velocity, but since mass for a particle is a constant, then really it's the speed that we're looking at. So we can't know the location and the speed. Emission spectrum of a particular element is always the same and used to identify the element, yes or no? Yes, that's true. Part of the Bohr model proposed that electrons in the hydrogen atom are located in stationary states or particular orbits around the nucleus. And the Bohr had those very specific orbits around there with very specific energy differences that led to the spectrum, the hydrogen spectrum, that he was able to predict. And then D, an orbital is the volume in which we are most likely to find an electron. That's what we talked about today in class. Your orbitals are your probability density for that the Schrödinger equation. It's where you're most likely to find an electron. So all of those are in fact true. Questions on any of those? Those are always hard to do, especially when there's an all the above. Those. They try not to write too many of those, but every once in a while I throw them in. Let's see, number 25. Did the term per photon mess you up? Okay, good. Because anytime we calculate the energy, it's always per photon. Okay, so we want to calculate the energy of the light emitted per photon by a neon sign with a frequency of 4.89 times 10 to the 14th hertz. Okay, so 24. So let's write down what we know. We know that the frequency is equal to 4.89 times 10 to the 14th hertz. Sorry about that. There's a little spittle there. This came flying off my tooth. Yeah, I'm going to have to go back through and edit this thing. Now I forgot what problem I'm on. I'm on 25. There we go. So we know that, and since we're dealing with light, we also know that C is equal to 3.00 times 10 to the 8th meters per second. Okay, so what are we looking for here? We're looking for energy. Well, it turns out we don't really need C, do we? We know the frequency because we know that E is equal to h nu. So Planck's constant times the frequency is equal to the energy of the photon, and we know h, so h is equal to 6.626 times 10 to the minus 34 joule seconds. How many of you memorized that after the homework? Yeah, I thought so. Yeah, we use it a lot in this unit. Okay, so we're going to just plug and chug there. We're going to say 6.626 times 10 to the minus 34 joule seconds times 4.89 times 10 to the 14th 1 over seconds. And our seconds cancel, leaves me only with joules. And I end up with an energy here of 3.24 times 10 to the minus 19 joules. Okay, remember when you're dealing with visible light, okay, so if it's giving you a color of light that's in the visible, like orange or yellow or red or green or something, your energies are always going to be in that 10 to the minus 19 range. Your frequencies are going to be in the 10 to the 14th range, and your wavelengths are going to be in the 400 to 700 nanometers, or 4 times 10 to the minus 7 to 7 times 10 to the minus 7 meters. Okay, that's where all that's going to fall. So if you get some really wonky, 10 to the minus 56 exponent, you did something wrong. All right, questions on 24. 5. Sorry. We go that one? 26. Yes. So you guys did so good on these and clicker questions. If it was math, you guys rocked. All right, 26. Okay, so calculate the wavelength of an electron. We have a mass equaling 9.11 times 10 to the minus 28 grams. We have a velocity going 3.66 times 10 to the 6th meters per second. Man, can you guys hear it rain out there? That's rain. That's pouring out there. Okay. And then we also need value of H. .626 times 10 to the minus 34 joule seconds. Okay, so do we have an equation? We're looking for wavelength. Do we have an equation that relates wavelength to all these values? We do, thank you. We have the de Broglie wavelength equation. So we have lambda is equal to H over mv, and that is a v, not a nu, so it's velocity, not frequency. Okay, so we're having a problem here with one piece of our data. What is it? It's our mass, isn't it? Our mass here is in grams. But if you're dealing with joules, what's the mass unit in a joule? It's a kilogram. So we've got to convert this into kilograms for our mass of an electron. And you might remember that because we've just had it a few times in class and in problems. So that's 10 to the minus 31 kilograms. Okay? So if not, you could go through the gram to kilogram conversion to get the same answer. So now we just plug that in and we get 6.626 times 10 to the minus 34 joule seconds all over our mass, 9.11 times 10 to the minus 31 kilograms times our velocity, 3.66 times 10 to the 6th meters per second. And when we calculate all of that out, we get 1.99 times 10 to the minus 10 meters. Whew. Questions on anything? Anything I did there throws you off? I maybe forgot to convert to kilogram. So if you want all those units to work out right, you need to break a joule out into its base units, kilogram meters squared per second squared. And because that has a kilogram unit in it, we've got to get the mass unit to cancel. So I've got to convert that mass to kilograms. Yeah. And then the meters per second cancel, the other second cancels, and just leaves it with meters. All right. You might want to see 27. I'm not going to go through that one because it's pretty much the same as what we just did. You're just solving for mass. You're going to get that mass in kilograms. Then you just need to solve for it in grams, convert it to grams. So you should get D on that. So I'll jump to 28. So number 28.
Yeah,
Okay, so third principle level. What does third principle level mean? N equals 3. That's all that means. N equals 3. That's your third principle. That's your principal quantum number N. So your third N is 3. So I want to know how many possible values of L can we have. Remember, the number of possible values of L are equal to the value for N. So for N equals 1, you have one value of L, 0. For N equals 2, you have two values of L, 0 and 1. And for N equals 3, you have three values of L, 0, 1, and 2. So the number of possible values of L are always equal to N. Just remember, they start at 0 and go up to N minus 1. Okay, so the correct answer there would be E3. 29. Okay, so Rydberg equation. How many of you had lab tonight? A few of you, was that fun? Was that kind of a fun lab? No? I thought it was a fun lab. All right. So determine energy change associated with the transition from N equals 2 to the N equals 5 in the hydrogen atom. So we want to set up this equation here. We have E is equal to negative 2.18 times 10 to the minus 18 joules times 1 over NF squared minus 1 over NI squared. Now I've got a couple emails because I know in the homework they gave you they gave you a different version of this equation, and rather than energy they gave you 1 over wavelength, and then they gave you a different value of R. It's still the same R, it's just in different units. It's in inverse meters, which, believe it or not, is an energy unit. An inverse distance is an energy unit. That always messes with me too. But it's just for calculating 1 over lambda rather than energy. It's still the same equation. So it just depends on what it's looking for. If you're looking for energy, this is the much better way to go. You could do it the other way. Just once you get lambda, you just have to go through and convert it into an energy.
So NF would be the final N value and NI the initial.
Exactly. Where it ended minus where it started.
Got it.
Yep. So you want to look at that transition carefully. Where did it go from and to? Yep, exactly right. So we know here it went from 2 to 5. So 2 is my NI. So let's plug everything in. So we're going to have negative 2.18 times 10 to the minus 18 joules times, so 1 over NF, so that's 1 over 5 squared, minus 1 over 2 squared. Okay, and so I take 1 over 5 squared minus 1 over 2 squared and get a value, multiply that by negative 2.18 times 10 to the minus 18 joules, and I get a value of a positive 4.58 times 10 to the minus 19. Okay, so that would actually be A there. Now, what is the fact that I got a positive energy value? What does that mean? That's right. It means the energy was absorbed. The plus and the minus in front of the energy term just tells you the direction of energy flow. And then the value of that number just says how much energy it was. Okay, if it were negative, that means that energy was emitted. Positive means that it was absorbed. Questions on that? All right, number 30. Yes, so very much same kind of problem here. It's another Rydberg equation. So we're going, we're looking for the wavelength of light here. So we're going from n equals 1 to n equals 3. Okay, so I'm going to use the energy one again, just because that's the one I usually use. Okay, so we're going to have negative 2.18 times 10 to the minus 18 joules times, we get same equation as up here. So here my n final is 3. So I have 1 over 3 squared minus my initial is 1 squared. Okay, so we've got that. So we get an energy here, and we calculate that out, of 1.9377 times 10 to the minus 18 joules. It wasn't asking for joules, it was asking for wavelength. But now that I know my energy, I can plug that into my equation here. So I know that E is equal to HC over lambda. Thank you. That helps me relate my energy to my wavelength there. I can solve that for wavelength. Now I have wavelength is equal to HC over E. I can plug all of those in, so I've got my Planck's constant there, 6.626 times 10 to the minus 34 joule seconds, times my C, 3.00 times 10 to the 8th meters per second, all over the calculated energy there, 1.9377 times 10 to the minus 18 joules. You can see my joules are canceling, my seconds are going to cancel. It's going to leave me with just meters. Great, I'm looking for a wavelength. Meters is a good unit for wavelength. And when that comes out, I get 1.0258 times 10 to the minus 7 meters. And it's looking for, all my answers there are in nanometers. And when I convert that into nanometers, I end up with 102.6 or 103 nanometers. Questions there? Okay. And last one, number 31. Yes, so looking for the M sub L. Possible values of M sub L for a d orbital. Okay, to get M sub L, we need to know what L is equal to. So what's the L value for a d orbital? Remember, so L equals what? 2. We've had that today. Okay, so if L equals 2, that means my M sub L values can go from plus L to minus L. So we can go from minus 2 to minus 1, 0, plus 1, plus 2. Those are all allowed values for M sub L when L is equal to 2. Okay, so the answer there is B. All right. That is all of the problems there. We've finished with 5 minutes to spare. Okay, I'll be in and out of my office tomorrow. If you guys need help, come on by. Otherwise, the best of luck to you on that exam tomorrow.